Assalamualaikum. So for this video, I will cover on the control valve, gain and transfer function. Okay. So for the OB attainment, basically this chapter is mapped to PO number 1, which is apply knowledge of mathematics, science, engineering fundamentals, and engineering specialization to solve complex engineering problems. The course outcome for this topic is CO number 1, which is select suitable control element for a particular control system. Okay, so we start with the control valve gain and transfer function. So basically, gain, the one that we learned before, is a change in output divided by the change in input. So basically, the output of valve would be the flow. The input of the valve is the controller output signal. So basically, in percent controller output. So we can say that the equation for the gain of the valve, which is KV, is equal to dF over dm. So basically, dF is a flow, dm is a control output signal. So the unit is GPM over percent CO, or LB per hour, square feet hour. Okay. So the valve gain obtained from 3 terms. So basically, it will depends on the valve position on control output, depend of the flow coefficient, which is CV, on the valve position, depend of the flow on the flow coefficient, which is CV. Okay, so these 3 terms, basically this KV, the first term is this one, valve position on the controller output. This one is the flow coefficient CV on the valve position, and lastly is flow on the flow coefficient. Okay, so for the first term, which is dependence of valve position on controller output, okay, we simplify the conversion of percent control output to fraction valve position. So basically this one, the dependence of valve position on control output is equal to the fractions valve positions over 100%. So this is plus minus negative, plus minus. So the plus signs, positive sign is for valve fill close, which is air to open. The negative sign for valve fills open, which is air to close. Okay, so the next term, which is dependence of the flow coefficient on the valve position. So for the linear characteristic, so the dependence of flow coefficients over valve position is equal to CV max. For the equal percentage, the dependence of flow coefficient over valve position is depend on the ln alpha CV max alpha to the power of Vp minus 1. So in other words, we can simplify to this one. Okay, so the last term, which is dependent of flow on flow coefficients. So we have two type of liquid services, which is constant valve pressure drop and variable valve pressure drop. Okay, for the constant valve pressure drop, you may use this formula. So the dependence of flow over with the flow coefficient would be the square root delta PV over GF. This is a specific gravity. This is the pressure difference flow through the valve. Okay, so this is the formula for the variable valve pressure drop. So basically, there is a few terms that been insert inside this formula. So basically, KL, this one is for the constant friction coefficient, this KL. Okay, the delta PO here is a delta PV plus with delta PL. So basically, the delta PV is a pressure drop between pressure drop of the flow that flow through the valve. Delta PL is a pressure drop in the line. Okay. Okay. So next is a constant valve pressure drop. So we have a value of gain just now. Okay. Basically, for the kV, will be equal to 1/100 CV max time with this one. So the last formula would be max flow over 100. So it depends on the question given to you. If you get the information on the flow max, you can directly use this formula. If you get the information on the CV or delta P or specific gravity, you can use this formula. Otherwise, if you get this value of W max, basically W max is a mass flow rate. Okay, you can see the units here, pound per hour. So next is the gain of valve with equal percentage characteristic. Okay, for same goes like previous. Okay, we adapt the characteristic equations. In here we adapt this one, and in here we adapt this one to the kV formula, the gain of the valve. So the last equation would be negative or plus ln alpha over 100. This is the flow time with the flow. So you also can use this formula, which is negative plus ln alpha W bar over 100. Okay, it depends on the information given inside your question. Okay, so for the variable valve pressure drop, okay, because we need to adapt the equation from the variable, the dependence from the variable for the variable valve pressure drop. So this one lah, this part. So the kV value would be this one. The kV equation would be this one. It can be simplified, become like this lah. Okay, for the gain of valve with equal percentage characteristic, we adapt the equal percentage characteristic to this gain of a valve equations. The equation would be like this. Okay, we also can simplify, become like this. The final one become like this. So again, it depends on the information given inside your question, with which type of equation that can be used for you. Okay, so now we try to do question number 1. Just now you already see all the equation related to each of the term. Right now we try to do the example. So the example wants us to find the gain and the valve positions. Okay, so basically from the previous topic, we learned to calculate the valve positions. Valve position is equal to CV over CV max. So the valve position would be (500 over 2000), 0.25. Okay, so we need to consider both valve with linear characteristic and equal percentage. So I try to do for the linear first. So we can use the formula given from the previous slide, which is kV is equal to negative plus 1/100 CV max delta PV over specific gravity. Okay, for the specific gravity, inside here given you with the density of the liquid, which is 800. So for the specific gravity, the standard density of liquid depends on the density of water, which is 1000 kg per meter cube. So you divide for the GF, you divide 800 with 1000, you will get 0.8. Okay, so we try to insert all the value given. So negative plus 1/100, this is 2000. So this is delta PV would be the inlet pressure and outlet pressure. This is the inlet pressure that enter the valve. This is the outlet pressure that leaving the valve. So the difference would be 20 divided by 0.8. Okay. So from here we try to calculate. Okay, you may calculate together with me. So the final answer would be 100. The value of kV would be 100. Okay, this is for linear. For equal percentage, maybe I can write here. So for the equal percentage, we will use the formula of kV negative plus ln alpha over 100 CV bar delta PV over specific gravity. So you insert the value. Ln alpha would be given here 50. Over 100. CV is 500. And the delta PV same 20 over 0.8. Okay, let's calculate with me. The answer would be 97.8. Okay, so finish on question 1. So we move to the transfer function. So basically this is the transfer function for the valve. GV is for valve. Okay, basically this is the block diagram of a control valve. Basically this one is a valve, this one is a valve. So the one that the input enter to the valve is the controller output, which is M in terms of percentage. So the output from this valve is a flow in terms of gallon per minute. Okay. So basically this kV is a valve gain. This is the time constant of valve actuator. Okay. So we try to do question number 2. So question number 2, using the valve gain obtained in question 1, write the transfer function of the valve if the time constant of the valve actuator is 0.3. Okay, so now we draw the block diagram of the valve, okay, which is, this is GB, the flow in is controller output, the flow out is the output from the valve would be the flow. So the transfer functions is kV over tau s plus 1. So basically we have the value of kV for the linear 100 over, so the time constant is 0.3 minutes. 0.3 minute you need to change to second because the time constant is in second. So 18 second plus 1. Okay, this is for linear. For equal percentage, sorry, this one is S, but the unit for time constant is second. Equal percentage, kV over tau s plus 1. So GB is equal to, right now we get 97.8, right? Okay, so this is 18 second plus 1. Okay, so that's all for question number 2. Okay.